talk about a concept that's relatively new in Java. And this is something that is going to make a huge difference in terms of how we build applications. And the impact of this, I'm going to say the power of Java 8 was it changed how we develop applications using the functional programming capabilities. The power of virtual threads, on the other hand, is about how we deploy applications in terms of the power we can gain from the active deployment of application. But I want to talk about this with a few different examples in here to see how this changes and what power and benefit we're going to get for it. But I want to talk a little bit about these three concepts that is often confusing for a lot of us. And that is the concept of parallel and the concept of concurrent and, of course, asynchronous programming. So the question is, what is parallel? What is concurrent? And what is asynchronous? You got it right? Because I just demoed it for you. And I demonstrated what parallel means and what concurrent means, in case you didn't notice it. I'm thankful I can walk and I can talk in parallel. I don't have to stop talking to walk. I don't have to stop walking to talk. So I can walk and talk in parallel. I can't, I shouldn't drink and speak at the same time. It's very impolite. It could also be very dangerous to health. I could choke up. So I can talk and drink concurrently, not in parallel. So parallel tasks can go at the same time. I can keep walking and talking in parallel, but either I can speak or I can drink, but not both at the same time. But I'm not asking you to sit here and watch me empty this full bottle and then say all the words I want to say, because I will be sequentially drinking water and sequentially saying the words. But I'm concurrently saying the words and drinking water. So what that means is, given a unit of time, both these tasks progress during the duration. But given a thin slice of time, only one of those two is happening, and that's concurrency. So the parallel and concurrency usually go hand in hand, but parallel simply means you are able to use multiple resources in general. Like I'm using my legs for the walking and my mouth for talking. So that can happen in parallel. But on the other hand, concurrency usually means you want multiple tasks to progress at the same time, but they have a resource contention. So they, so to say, time share. And I can use my mouth to drink some water, or I can say words, but not both at the same time. So we talked about parallel and concurrent. And as it turns out, over the years, languages like Java has been focusing very heavily on parallel processing and concurrent programming. But the world we live in is very different. But I know this is really hard to say it, but I'm going to say it once. And if you ever tell anyone outside this room that I said this, I will deny it. JavaScript got it right. I said nothing. So essentially, if you really think about it, the world really heavily relies on asynchronous programming. Why? Because as much as we thought parallel and concurrent are important, they are. But what does the business world rely upon? You make a request to a remote service, web service or microservice. You access files in a file system. You query data in a database. You log. So anytime you perform any form of I/O, you really are performing a task that is outside of your CPU. And when you're outside of your CPU, the question is, what do you want to do with the CPU is the question. So let's talk about that a little bit, about what does it mean to be asynchronous. So the first thing we need to understand with asynchronous is the following. And that is, when it comes to asynchronous, the key thing we want to think about here is this. When you perform a task, right? So you can say, when you invoke a task that needs to return a result, you have to block. There is no other way, correct? I go to the coffee shop and I say, could I have a cup of coffee, please? And then I'm gone. And they make the coffee. It's like, where's this dude who ordered coffee, right? So I can't just order coffee and walk away. There's no way. I'm never going to get coffee if I do that. So if you ever perform a task and you need a response back from the task, a result back from the task, you have to block. There is no other solution, period. So then the question is, when we say, asynchronous, you could say, right, asynchronous is non-blocking, but what does that mean? So the question really is, if it is non-blocking, I don't get it. Because I can't just say, I want to have a coffee, please. Boom, I'm gone. Then I'm never going to get the coffee. So every task that requires a result has to block, but asynchronous means non-blocking. What does it mean? So the answer to that question is, fundamentally, we want the task. So we want the task to block, but not hold the underlying thread hostage. That's what it means by non-blocking. So when we say non-blocking, we always want the task to block. But in Java, what happens? When a task is being executed on a thread, and the task says, hang on, I need to wait for I/O. And the thread says, no worries, I'll be right here waiting. And I will block and wait with you. Let's translate that to English. Inefficient. Because when your task blocks and your thread blocks, what happens? The thread is not available to do the work. So what do you say? You say, wait, the thread is stuck. It's not running. That sucks. So let's create more of that. How is that logic working, right? Because the thread is not working well, so let's do more threads. This is like employee we hired is not working, we'll hire more employees, right? So the point really here is, if the thread is not working, we need to address that, but not create more threads. But why are we creating more threads? Because we want more responsive code. We want maybe other tasks to run, so we create these more threads. But the more threads you create, what happens? There's a limit to how many threads you can create. So how many threads can you create fundamentally? Well, as it turns out, there's a limit to number of threads you can create. So the question is, how many threads should we create is the question. And the number of threads is less than or equal to, and you can draw upon a little formula. And that is, it is the number of cores divided by 1 minus what's called the blocking factor. So what in the world is this blocking factor? We'll come to that in a minute. Where the blocking factor is the percentage fraction of time your task is blocked on I/O. So 0 less than or equal to blocking factor less than 1. So think about it for a minute. You may say, whoa, the number of threads I can create is based on memory, right? That's true. To some extent, that's true. But beyond memory, I actually worked for a company a couple of years ago. And I found out that working for them is like Christmas every day. I wish I had found them before in my life. Because any question I asked them, they always responded back with a question. And I asked them, how much memory does this machine, developer machine, have? And their response was, why, that developer machine you're using only has 1 terabytes of main memory. But if you want more, please let us know. I was like, wow, 1 TB of main memory, right? And if you want more, please let us know. And then I said, how many cores does this have? They said that only has 1,000 cores, but if you want more, please let us know. I'm like, where are you guys so far, right? You can keep getting more machines, right? So my colleague at the client side said, we want to make this faster. And they had an extremely tough computation, a lot of mathematical operations to do. And we took a sample. And that sample to run sequentially took 30 minutes to run. And the job given to me is make it faster. And I'm taking the sample data, and I'm going to make this faster from 30 minutes. So I worked to parallelize the code. And here I was proud, patting myself in the back. And I called him and said, did you notice that? I parallelized it. It runs faster. And he said, how fast does it run? And what was running 30-minute sequential now ran parallel in 5 minutes. And I was like, isn't that cool? I brought it down to 5 minutes from 30 minutes. And my colleague was not there to be pleased so easily. And he said, how many threads do you have? Oh, I'm using 1,000 threads. And you know why I was using 1,000 threads? Numerator, number of cores, was 1,000. And he said, I want 2,000 threads. I said, no, you don't. And he said, I'm paying you and I demand. Okay, you win. So I bump it to 2,000 threads. The code that took 30 minutes to run sequential and 5 minutes to run in parallel with 1,000 threads, now with 2,000 threads took 90 minutes to run. Why? Why would it take 90 minutes to run? After all, you get more threads, isn't it? If you have 4 cores and you create 4 threads, the 4 threads are running on the 4 cores, off by 1 error, 5, right? So you got 5 cores and you got 5 threads running on it. Now I create 10 threads in this example. What's going to happen? There are 5 threads running and the other 5 threads are watching. I can run, but I don't have a core to run. But these threads are not like the normal population. They're like monks. They run and they look around. Oh my God, you're waiting. How rude of me to be running when you are waiting. Please. And the other thread is like, thank you, you're very kind. Jumps on it. And then, oh my gosh, you're waiting. How rude of me to be running. Right? This is what happens when you put monks on the treadmill. They're too polite. Your turn, please. No, your turn, please. That's what the thread are doing, right? They're trashing. And while they're trashing, your real work is still pending. 90 minutes later, we got it done. Well, how many calories did you burn? Yeah, never mind. So the point really is that when you have more threads than the number of cores, you lose performance. That's when your tasks are computation intensive. But what if they're I/O intensive? So for computation intensive, so you can say for computation, right? So computation intensive, blocking factor is equal to 0, right? There is no time it's waiting on I/O. There's no I/O because it's computation intensive. So number of threads is less than or equal to number of cores. Because 1 minus 0 is 1. 1 is gone in the denominator. So that's number of cores. For, you could say, so for I/O intensive, where you could say blocking factor is 0.5, what do we know? number of threads is going to be, in this case, you could say, that is 0.5. So 1 minus 0.5 is 0.5. Bring the 0.5 to the numerator. That's 2 times the number of threads. If the blocking factor is 0.9, 1 minus 0.9 is 0.1. That is 10 times the number of threads. Now, let's talk about this. If your machine has 1,000 cores, is that a lot? That's pretty big size, isn't it? If your machine has 1,000 cores, and if you are performing I/O, let's even push it to a 0.9 as a blocking factor. What does that mean? You can have a total of 10,000 threads, which means at any given time you can do 10,000 concurrent requests. What if you get 20,000 requests? 10,000 is being processed, the other 10,000 is waiting because it cannot get on it. There's not enough threads, isn't it? But I want to process 20,000 requests simultaneously. What should I do? Scale horizontally. What happens when you scale horizontally? The cloud providers are very happy because your boss is busy talking to their boss, and they make the trade deal, and your company is spending money, and your pocket is becoming poorer by the minute. Why are you spending so much on your cloud? Oh, we got to scale. Why do you have to scale? Because threads suck. Because they're held hostage. Because when a request comes in, and when my thread is busy processing the request, what is the thread saying? Thread is like, hey, what are you doing? Waiting? Now, anyone in this room who is a parent of a toddler, or you have a little niece or a nephew, some little kid in the house, what is the first rule of parenting or guarding children? What's the first rule? What was that? Keep them big. Oh, you are a wise man. What is the second rule? But this is the myth. You think you are keeping them busy. When you hear the children talk, you realize they were keeping you busy, right? Absolutely. So what's the first rule of parenting? When the kids sleep is when you get your work done. What is the rule of bad parenting? The kid says, I want to sleep. Good idea. Let's sleep. And you sleep next to the baby. Nothing gets done, right? So what is the thread saying? The thread says, hey, here is a work to do. Oh, I got to do I/O. So I'm going to take some time. And the thread is like, take your time. What are you going to do? Just sit and watch. Now imagine you go to a good restaurant. And you go to the good restaurant, the waiter comes to you and says, hey, what would you like to drink? And you say to the waiter, not sure. What is interesting to drink? Oh, we got this, we got that, we got this. And the waiter gives you a list of things. And you say, you know what? I'm not sure what I want to drink. What does the worst waiter in the world do? The worst waiter in the world says, oh, so you're not sure what to drink. And pulls a chair, sits next to you and says, tell me what's your mood like today? How's your day going, by the way? What will happen if the waiter pulls a chair and sits next to you? The folks on the other table are extremely angry because they've been waiting on stuff and they're not being provided, right? So what does the good waiter do? The good waiter says, hey, you know what? Why don't you think about what you want? I'll be right back. Gone. Here's the irony. Waiters don't wait. They are called waiter because they make you wait. So what if Java threads are like waiters rather than waiting? So what if what if the thread says, hey, you're going to do I/O, right? Yep. Why don't you go do it? I'll be right back. It's gone. While your task is blocked, the thread is no longer blocked. The thread can go do other work, and your task is blocked and waiting. The I/O is complete, and the task says, I'm ready to run. Pull one thread and give it. Hey, which thread is it? Do you care? With all respect, do you care? You're in a restaurant, and the waiter comes to pour water. You say, stop it. You're not my waiter. That's the best way to get kicked out of the restaurant, because you should be happy they gave you water. You don't say, you don't look like my waiter. I insist you go back, send my waiter with water, and I want water but from nobody else. But with all respect, right? You don't care which waiter serves you. In fact, in a good restaurant, one person takes your order, another person fulfills it, a third person pours water, sometimes in the water cup, but like the last time, it was on me. Maybe that's the way they keep me cool. It was a very embarrassing experience, but nevertheless. But the point really is, you could have multiple waiters switching around. So there is no reason for you to have the affinity of the thread. And as a result, you can get better scale. So the idea here is, what happens in that case? If we're able to do that, then we don't have this limitation. Why not? Because threads are no longer blocked. Threads become non-blocking. When threads become non-blocking, your task is waiting, but your thread can take the next one. Like, for example, it was literally 2 a.m. I have been on a long flight, and I walk into this hotel, and I am sleepy. I need to go lay down. I've been on the flight for 24 hours. Not here. This is a nice hotel. I'm talking about a hotel in another part of the world. And there is one person, the clerk, and there is one customer at the 2 in the morning. And the customer is standing in front of the clerk, and I'm the guy who travels with my passport in my pocket, literally. Because I know when I travel, I can't leave this anywhere else. So it's literally here. So I'm going there. Okay, I'm ready to check in. Here's my passport. I'm ready. And this guy in the front, I want to check in. And the clerk is like, I need to see your passport. You need to see what? I need to see your passport. Oh, passport. And that's when he searches a binary search. And I'm like, kill me now. Can I check in, please? But the clerk, he could have said, why don't you go through a nice algorithm, maybe a quick search next time? But while you're doing it, let me switch over here and help the next customer. That would have been nice. But instead, he wanted to be entertained by the binary search. And I'm like, why? That is lack of efficiency. And that's exactly how threads work. And until somebody else came and rescued me, there's not going to be any movement of process. Your threads are waiting. So you can scale horizontally, or you can scale by making threads non-blocking. So this formula is no longer valid if you can create non-blocking threads. And we'll see how in a minute. So we talked about behavior of threads. That's what we did. You can observe the threads just to get a feel for it, right? So why don't we do that, just for the fun of it? So let's go back here, and we'll say max equal to, let's create 1,000 if you don't mind. And we'll say for an int I equal to 0, I less than max, I plus plus. And let's simply say a new thread, and we'll call this one as a thread in here is equal to a new thread, right? So then thread.start, and we'll start the thread right here. So once we start the thread, what are we going to do in this case? So in here, I'm going to simply say, let's go ahead and say, sample do work. So what does this do work function do? So let's do a public static, void do work, and the do work method simply says try thread.sleep for about 5 seconds. And that's all it's doing, right? So literally, this thread is not doing any real work. All it's doing is just taking a nap. When the task is sleeping, what does the thread do? The thread says, wow, great. And it sleeps with the task. They both are sitting there, right? If I create 1,000 threads, you can imagine the amount of snoring you're going to hear from this now, right? 1,000 threads snoring for 5 seconds right there. So that's our code that's going to run. But I'm going to go back here, and just for us, I'm going to simply say here, I'm an old guy, so to make it work for me at the speed at which I work, or the lack thereof, I'm going to go ahead and put this as a 20-second delay, and then I'm going to say over here, so we can observe this, I'm going to say starting. So you can see clearly when it actually started, right? So if I run this code, what am I going to observe is the question. And mind you, I'm not doing anything useful. All I did was call sleep. That's all I did, right? Nothing really exciting. That's all we did. So let's let that run in the background. So I am going to go back here, and we are going to say run Java, and I'm going to run this code and see what it does. So it started it. So then I say JPS. You can see the two of them running. I'm going to assume it is this one, the second one. Actually, you know what? I'm going to just wait for it to die, and then we'll come back and look at it just to be sure, and we'll run through this again. So 20 seconds, right? That's a long time, I guess, suppose. So JPS, that one is still running. Let's kill that. So 87061. There we go. All right. So I'm going to go ahead and start this one. Maybe in this case, I can even say, yeah, let's wait for 20 seconds. Let's do that. So I'm going to say run Java C. Go ahead and run that code. Started. Here's JPS. That's my process. So JConsole, and I'm going to start JConsole, and I say go for it, and it started up. It connected to it, as you can see, and I say threads. I'll read this for you. It's a little hard for you to read. It said 16, right? 16 threads. That's JVM creating 16 threads. Did you notice what happened? It shot up to 1,016 threads. You know why? Because 16 threads used by my JVM, and my 1,000 threads came in, right? So it shoot up, and if you notice how many threads it used right there, 1,000. You can see that one. So we used 1,016 threads. What's the moral of the story? If I create more threads are going to use resource, and it's going to not be able to scale beyond that. I got to scale horizontally, right? Because the formula that we talked about comes in. I cannot keep creating more threads. I'm going to run out of it eventually. And as a result, I got to scale horizontally. So far, so good? So then you ask the question, but wait a minute, you say, wait a minute. Why am I, is the question, right? Why am I creating more threads when this is blocked? Why can't I non-block the thread is the question. So we talked about the impact on scalability and consequence. So what are the consequences of this? The first consequence, we have to scale horizontally, which means you got to keep paying these companies more money to scale. They're happy with us. But the question is it where you want to spend your money on? Second problem, environment. You have to run bigger form of computers, servers. That has an environmental impact, isn't it? Why are you running more servers? Because I want to process more requests. But why can't you process that with less? Because my threads get blocked and they're just doing nothing. This is the equivalent of a restaurant being told, you got to hire more waiters. Why? Because the waiters you hired are sitting at the table rather than doing the work. That would not be a good restaurant, right? They will go out of business doing that. So we got to think a little differently, right? So what can we do? Now, we want non-blocking execution. I'm going to skip the Kotlin part here. But what are we going to do? Now, before I answer the question what we're going to do, I want to take a slight detour. And this is where I get excited. When you look at problem solving, sometimes somebody comes along and radically changes the way we think. So if you ask me, we gotta give an award in computer science. Whom should we give it to? My vote will be to one person because he said something that affects what we do every single day. There's not a single day, I promise you, that you ever do. You may not realize it. You may not think about it. But I promise you, not a single day you ever write code without applying what he said so profoundly. His name, he passed away, his name is David Wheeler. David Wheeler was a British computer scientist. And what did David Wheeler say? David Wheeler said, in computer science, he said, you can solve almost any problem, he said, because he's too modest, by using one more level of indirection. This, to me, is the most profound statement ever. Because you can solve almost any problem, he said, by having one more level of indirection. And I guarantee you, you cannot think of a paradigm in programming where you don't have this level of indirection. Let's give it a try. I'm going to talk about procedural programming, like the C of the word, right? So this is the paradigm. And what is the level of indirection in this, right? And this is the pointers. We all have tried it, right? At some point. So you're doing procedural programming, like in C, and what do pointers do for you? A pointer says, I am pointing to this function right now. And you call the function using the pointer. And then you say, here, point to this other function. And you're calling to the same exact pointer. But you're calling a different function, isn't it? So rather than calling the function directly, you call the function through the indirection. That is what is indirection, isn't it? You're not calling what you want to call. You call it's like my people will talk to your people, and they will talk to you, right? It's a level of indirection. So you are routing through one more level in this case. So in procedural programming, pointers give you that level of indirection. In object-oriented programming, so what do we do in object-oriented programming? We have to have a level of indirection in there as well, isn't it? Thank you. You nailed it. You bingo. It's another P word. That's called polymorphism. Beautiful. You nailed it. Polymorphism. What does polymorphism say? The method you call is not based on the type of the reference at compile time, but it's based on the type of the reference at runtime. So I have a reference. It belongs to a vehicle, but at runtime, it is of type car, or it's of type truck. So the method I call is either on car or on truck, not on vehicle. That's level of indirection. So polymorphism gives you the level of indirection, right? So you make the call using same reference, but at runtime, it knows to go to different places. That gives you that indirection. So that makes you wonder, right? And that is, we got to have something like this, right? In functional programming, we need to have indirection too. Almost, yeah. Which is what, maybe we can take a slight detour if you don't mind, right? So I apologize to you for this, because I'm a big fan of dad jokes, because that's how you make your children feel the pain, by telling dad jokes, right? And they cringe. So here's one for you. Are you ready? You should answer first thing that comes to your mind. Shouldn't hold back. Promise? Okay. All right. What is the most favorite animal for functional programmers? Cat. I don't know why, but what else? Come on. Cannot think of an animal? Giraffe. Ooh. Not sure why, but yes. What was that? Python. It's okay. You can say the word. I know this talk is Java related. How do you tell others you're a Python programmer without telling you're a Python programmer? I see what you're doing there. Python. Mm-hmm. Somebody said, oh, camel. You know what it is? It's lambda. Okay, I apologize. Okay, so you can achieve this by using lambda expressions, which is really the function references that you said. So lambdas give you indirection. How do lambdas give you indirection? Because you're saying, I give you a lambda, you can call it, you can throw it away, you can keep it and call it later, or you can pass the lambda to somebody else who wants to use it. So lambdas can float around, and in different calls, you can pass different lambdas. So using that function reference, you can achieve polymorphism. So you could say lambda plus function values, as some languages call it. So what is the moral of the story here? You can solve this problem by having a level of indirection, isn't it? So the question is, wonder, what level of indirection can help us here? And that is called virtual threads. Virtual threads are a level of indirection. That's it. And when you look at it that way, you're like, okay, that makes sense now. Because virtual threads are just another level of indirection. So rather than running your task on a thread, run your task on a virtual thread and let the virtual thread run on the thread. That's your level of indirection. So don't run on the thread. Run on a virtual thread, which in turn runs on a virtual thread, on a real thread. Imagine this about this amazing horse rider. And what does the horse rider do? The horse rider, she mounts the horse. Right there, she's on the horse. She mounts the horse, and the horse is moving forward, and she decides she no longer wants to ride. What does she do? She unmounts from the horse. And when she unmounts from the horse, another rider can take the horse and run with it, right? The horse doesn't have to be stuck there. So the horse rider can mount, and the horse rider can unmount. So what do tasks do? task, when a task blocks the virtual thread that it is running on blocks. The virtual thread unmounts from the real thread. When the task is ready to run, the virtual thread that is running the task mounts on a real thread and moves forward. Very simple, right? Now, simple to talk about. A lot of work for them. But the point is, your virtual threads mount and unmount. They mount and unmount. So as a result, what happens? You will need fewer threads at the operating system level. And you can have more threads at your application level, virtual threads, that is. You want to prove it? Right? So let's prove it. That is actually true. And how do we prove this? So to prove this, here's the code we wrote a few minutes ago, if you remember. And I'm going to go back to this code. And I'm going to say, all right, so in this code, let's not create a regular thread. Let's not do that, right? So instead of that, let's say thread dot start virtual thread. So start virtual thread right there. And what are we going to do for this virtual thread? Sample do work. So we are telling the task, don't run on the thread, please. Run on a virtual thread. So you're starting the task on a virtual thread, right? And what does a virtual thread do? Mounts on a thread. And the task says, stop. I need to sleep. And the virtual thread says, no problem. We can sleep. But let's unmount and we can sleep. How many threads did our application use before, remember? 1,000. Keep that in mind. So I go back here. I'm going to run the code this time. And JPS again. Here is the ID. JConsole. Back to that. And let's open the connection. How many threads do we have here running right now? 16, right? Because it's not started yet. 16. Now, as time goes on, it says it finished. How many threads did this code actually use is the question. Not a whole lot. Okay, you're like, okay, let's try this one more time, can we? So let's go back here. And in this case, just for the fun of it, this is sleeping for 5 seconds. Let's make this actually a 5,000 threads. And back here, just to be sure, right? Go ahead and fire it up. So in this case, I'm going to start this again and ask for JPS again. And we got the process. So JConsole, start that and go for it. Here's the threads. Still at 16, as you can see right there. Still at 16. And at some point when the 20 seconds is over, boom, boom, right? That is 5,016, folks, if you noticed. Right there, 5,000, right? So that's 5,016. That's how many threads we used. I go back to the code right now in here. And what am I going to say? Don't use the threads. Use virtual threads. Yep. Is it computation or is it I/O? Well, you shouldn't use this for computation because what does computation do? There's no unmounting. You get no benefit. But if it's performing an I/O, calls a database, calls a remote web service, makes a microservice call, logs to a file, reads a file. Every one of them is no different from sleep, right? So, and the sleep is a little bit more acute because I'm really extending it to illustrate the point, right? So when we go back and run this code this time, and back here, let's bring the sample. So JConsole, run this again, look at the threads again, see what it says. It's 16 right now, right there. But when the 20 seconds is over, remember we're creating about 5,000 threads in this case, right? That's still holding up pretty nicely. What if I do real I/O? You're going to see a little bit more bump in it. But it's pretty interesting in terms of how it really didn't even cause much of a dent. And to your question, right, if I perform a real I/O in that code, that's going to be a little different. So if I were to go back here and say, let's say, in this case, import java.nio.file.star, and I'm going to say right here, rather than the sleep, you know what, I'll keep the sleep. Gives a little bit more control, otherwise things are too fast. So I'll keep the sleep. But in addition to the sleep, let's go ahead and say files.lines paths.get, and on which sample.java. So I'm asking it to read the same file we are in this case. So I'm performing a file I/O, right? What happens when you perform a file I/O? When I perform a file I/O, in fact, let's remove the sleep. Let's be bold. We'll see what happens. Get rid of that. So I'm asking it to perform a file I/O. That's what I'm asking it to do here. So let's see if that actually does anything. So in this case, oops, it's not size, right? Is it size? Count. So essentially, if I go back here one more time, and I use a regular thread, as we did a minute ago, just in all fairness, let's go ahead and run this again. And let's look for, let's close this. So come on. No. So JPS, here is JConsole. Run that again, and look at the threads. So once again, we're reading file I/O. We're not doing sleep in this case. So what is it doing in this particular example? That's what I was saying. This is a little too fast. And it really did not shoot up that much because the calculation, it's not going to take much time as it comes through and runs through here. But let me verify this. Yeah. So that's why I wanted to give a little bit of a thread just to illustrate that. Sorry, sleep, just to illustrate that. So if I say thread.sleep, and maybe 5,000 on this. So the point really is that as you go through it, it's going to exercise that. You're going to see the difference as it runs through, and you're going to see it's taking a little bit of time for it to execute. And on the other hand, if I were to use the virtual thread, you're going to notice that it doesn't actually occupy so many threads. Here it is. We can just look at it here. So that should actually shoot up now because we put the little thread. Again, that I/O is too fast. Maybe I can make a remote web service call. With this network, it may take a lot longer to get the response back, but you get the point. So back here, I'm going to say, don't use the thread. Instead, use a virtual thread. That's what we're asking it to run, right? So we'll use the virtual thread. So when I run this again this time, what is it going to do? So again, JPS, and pull that in. And that's a thread still running. And yep, not much. This is not taking a whole lot. You can see a little bit more than 16, right? Well, not quite at 15. That's all it needed. Why? Because it was like, yeah, you can sleep. I'll let go of the thread. And the thread is like, I can do more work. But here is the question, right? Here's the question. With this, let's do one more thing if you don't mind. Let's go back to thread. And I say not 5,000, but 10,000. 10,000 threads, right? I'm asking you to run with 10,000 threads. And in fact, just to make it a bit more fun, let's ask you to run without any delay on it, right? And what is it going to do? Boom, go run 10,000 threads. And at this point, when you're done with all of this, I could even ask it at the very end of this. I could say, here is a thread, and equal to null for a second. I can say this is the thread, and I can say thread dot join. I can wait, and of course it wants me to handle the exception. We'll just simply say throws exception on this. So when I run what I wanted to do, I forgot. So after this, I want to say output done, right? So say done, we're done. And at the end, say it's done. So if I were to run that code, you're starting 10,000 threads and you're saying go, and it's done. What if I create 20,000 threads, right? So 20,000 threads. So when I ask it to create 20,000 threads, what does it say? Out of memory error. Can't do this anymore. Why not? Because you don't have enough memory to keep creating more threads, right? So let's go back to 5,000 threads. So here is 5,000 threads. But instead of threads, I'm going to put virtual threads, right, in this case. So I'm asking it to create virtual threads. So thread is equal to virtual thread. Run that code. And we're doing 5,000 threads. No problem. You say, go 10,000 threads. It handled that even in the other one. So not a big deal. What if I said 20,000 threads? That failed, didn't it, for regular threads? And what does this say for 20,000 threads? When I run that, did you hear that? It said, why don't you give me something more challenging? Okay, 100,000 threads. We are creating 100,000 threads, right? And it says, truly, why don't you give me something more challenging? 500,000 threads. I feel like an auctioneer. Do you feel a little stress? You feel that? He is sitting on the edge of the seat right now. 500,000 threads. That's what we just did, right? And it's like, okay. One million threads. 1 million threads. And I showed this last time, and one guy said, what if you want more than 1 million threads? You can never make anybody happy, right? Everybody happy. I told him, if that's what you want, you got a bigger problem. You need to go talk to your architect. How many threads can you create? As many as you want. As many as you want, as long as the threads do I/O. You shouldn't use virtual threads for computation intensive. But we're talking about asynchronous, which is for I/O, not for computation intensive work. Does that give you a feel how this actually is able to be non-blocking? So how does this help us? So we saw how to use virtual threads, and we saw the usage of virtual threads and how it's able to keep creating more threads. So what's the bottom line? What's the benefit you get? You can perform I/O. You can make web service calls. You can perform logging. But when you do this, what happens? Let's imagine for a minute, like a Spring Boot application. So your Spring Boot application says, I got 1,000 requests coming in, And I'm going to make 1,000 I/O. Why? Because your Spring Boot application wants to talk to servers in the backend. It wants to talk to a database. It wants to talk to other services. And when they do, what do these 1,000 threads do? The 1,000 threads are blocking and waiting. I'm waiting for this to respond back. And in the meantime, all the other requests with their passport on hand are waiting in line, isn't it? Saying, I can process. Can I process, please? And it's like, nope, we're busy here. But here, a request comes in. It throws the request on the backend server and says, perform this I/O, go get this data. And what does the thread do? Immediately goes to the front. May I help the next request, please? Takes it, throws it in. May I help the next request, please? So now your queue is being emptied as the requests come in. And when this is done, that gets processed and the response goes back. So as a result, your server can scale on a single box. So somebody asked me the other day, they said, 2 questions people ask. The first question, oh my gosh, with this, is reactive programming dead? We love killing things, right? Is reactive programming dead? Hey, can you rejoice? No, is that dead? Maybe people have got hurt with that, right? Tell me it's dead. Well, you know the answer. What is the answer for such question? It depends. That's right. It depends. What does it depend on? If reactive programming meant, it means 2 things to me. It depends on what it means to you in your application, right? In some applications, it means one. In other applications, it means the other. If reactive programming means asynchronous, that's dead. I like the feedback, right? That's like little background music. Music by, I don't know, who's the famous musician now in the country? Pop. Better than that, right? So we have, if all that means is asynchronous, that's dead, right? But if reactive programming means not just asynchronous, but also back pressure. Virtual threads don't give you back pressure. That's not the concept. So question to you is, what are you using reactive programming for? Well, I could be using reactive programming for asynchronous. I could be using it for back pressure. If you're using it for asynchronous, quit using it. See? Back pressure is better for that. But if you're using it for back pressure, then this is not going to serve the purpose. That's one thing. So the second thing is, raise your hand if you have used completable future. Keep it up. I'm not finished my words. Raise your hand. Raise your hand if you use completable future happily. No, not one person. Because what did you understand from completable future? The first time you look at it, it's like, whoa, this is cool. I can write the functional pipeline. And you write it. And then you realize, this is the happy path. But what if something were to fail? Why would it fail? Because it's I/O. I/O means exceptions happen, right? And then you say, this is thenable, but then this is the exceptionally. And when you look at the code, it looks like this. And you're like, this is the happy path, that's the unhappy path. Has anyone here understood the code after you wrote it? No? Yes. This is unfortunate, isn't it? So I'm here to tell you the bad news. And the bad news is, let's put it here. And the bad news is this. With virtual threads now available, completable future has no future. That's it. Why would you suffer with that, right? So what is really dead is completable future. I love that kind of feedback. I love that kind of feedback. Absolutely. Say it again. Say it again. So, with virtual threads, there is no reason to endure that pain. As it turns out, what is functional programming really good for? When you deal with functions with no side effect. Where does functional programming miserably fall flat? When you deal with side effects and exceptions. One thing I will emphasize is this, and that is, to me, functional programming and exception handling are mutually exclusive. Yep. This in programming is called hope. It's a good thing. Yeah, and how are you feeling about it afterwards? Exactly. And that is the problem, right? We are putting these band-aids, that's called scotch-driven development. You put a little tape, and a little tape here, and then 2 weeks later, it's hanging a little bit on this side, more tape. And there's more tape on it than substance after that. Your code lacks cohesion, and every data you pass, you got to keep passing error or data. Becomes painful.
What you tell you to me about the execution, what it does to me that
This is called Stockholm Syndrome. It doesn't feel that bad. They were still feeding me 3 meals a day. But why? Because imperative style does that really well. And the beauty is, you can look at what we did here. We directly took this code here, and very nicely, we put a try, we did the I/O, and we handled the exception, and did whatever we want to do here. Clean. This is the place where imperative style really shines. So to me, we have to use the right paradigm for the right reasons. And imperative shines with impurity. Functional shines with purity. By keeping them separate, when you perform I/O with asynchronous, you're falling to a style we are used to. And that works nicely. When you write functional style code, you can focus on pure functions, and that shines really nicely. So we're able to create maintainable code on both sides. So what virtual thread did is it resets the leveling playing field. And it says, imperative is not always bad. There are times when it's the right solution, and let's use it when it is. Functional is great in some times. Let's use it when it is right solution. So we have two paradigms. We understand both, so we can leverage what is right at the right time. And as a result, we can provide it. So as a result, we can focus on asynchronous with imperative style. And here's the benefit. If I can spend 2 more minutes summarizing this for us. And this is what absolutely I love thinking about programming. Let's go back. In the past, right? In the past, way past, what did we know? We know the structure of a parallel imperative style code is very different from the structure of sequential imperative style. Oops. Right? Imperative style code. So in the past, in the old Java, right? You can say was. We all have seen that pain, isn't it? What happened? You wrote this code in imperative style, sequential, and somebody said, let's make it parallel, and you did, and you no longer can recognize the code anymore. You had a little photo taken of it, and you always like, it used to be so nice, nostalgic, right? And look at this monster, how it turned out to be. Let's see. Starting Java 8, the structure of parallel functional style code is the same as the structure of sequential functional style code. Thanks to, anyone wants to take it?
Okay.
What was that? Stream API, you got it. Thanks to the Stream API, right? Beautiful. Starting Java 8, one more time. We got another two minutes to finish. Starting Java 8, the structure of, you could say, the structure of, and here's the problem comes in, the structure of parallel, this is parallel asynchronous code is the same as, sorry, I'm mixing the words here. The structure of asynchronous functional, there we go, style code is the same as the structure of synchronous functional style code. Anyone wants to take a stab at it? Thanks to, who was it? That's right, completable future, right? But we all know what the problem of that is. And the problem of that is that you are writing code in functional style, it becomes hard to understand, hard to maintain it. The structure is the same, but it's not maintainable. So here is the final conclusion. And that is, starting Java 21, the structure, you could say, of asynchronous imperative style code is the same as the structure of synchronous imperative style code, thanks to virtual threads. And that is where we are with the power of how we bring these to an easy, understandable, maintainable code. So you can write it synchronous, and you can make it asynchronous. But how do you do that? Not by touching the code, but by changing thread to virtual thread. And if that's what you do, this is not changing. But if you're changing this, virtual threads become aspects in AOP. So you turn it to an aspect. You can control the aspect and change the behavior here. That gives you enormous power in how you maintain your application. Because you're not changing the code here, you're changing the strategy over here. And that gives you power as well. And that's why I'm excited about virtual threads. Hope that was useful. Thank you.